Okay, good morning, folks. I have 3 minutes past the hour, and it looks like the attendance list is converged, so let's go ahead and get started. So I don't have much in the way of announcements for you. Thank you to everyone who submitted homework 6. I think I have 5 of them in hand right now. Unfortunately, I am slipping further behind in the grading. I guess as we're getting into the more and more complex material, more and more of my time is being spent on creating the lecture notes and homeworks associated with them. So I'm going to have to do something different to make sure that I can catch up. But this is about where we stand right now. I have homework 7 designed, but I'm not ready to post it until I finish writing out all of the solutions to ensure that there's no wrinkles or unexpected problems on that. This is a homework on the Zeeman effect that we discussed previously. Before we get into a recap on the physics, are there any logistical questions or concerns that you would like to discuss? We seem to be running about a lecture and a half, maybe behind the schedule that we had discussed. We'll see what that does once we make it all the way through scattering theory. We're probably on track to have the exam in another couple of weeks. We're going to need to get through this week on scattering theory, next week to wrap up the rest of scattering theory, and then probably thereafter we'll go into the sample exam and then the exam. That's what I'm thinking for right now. Anything else? Okay, if not, then let's remind ourselves about the subjects that we were discussing the last week or so. We spent a significant amount of time after the first exam discussing time-dependent perturbation theory. We talked about the Drest propagator and how that appears in perturbation theory. And one of the main results that we discussed was Fermi's golden rule, which was a way of calculating the transition rate between some initial state and some final state at first order in perturbation theory. Fermi's golden rule specifically applied to potentials of this form, where the time dependence is given by a pure plane wave, e to the minus I omega t. And if the time dependence is e to the minus I omega t, we said that that is equivalent to absorbing a unit of energy equal to h bar omega. So the picture that I draw to go along with this is you have some quantum system that starts off in some initial state with energy E initial. It is absorbing a pure mode from the time-dependent perturbation with energy h bar omega, that if there is such a transition accessible to it, is trying to drive the quantum system from state E initial to state E final, whose energy is E initial plus h bar omega. That plus h bar omega, which is what's reflected in this delta function, corresponds to e to the minus I omega t. If you had e to the plus I omega t, then that would be a minus h bar omega transition that would be canceling out energy and trying to drive the transition down. The form for Fermi's golden rule was this. There were 2 ingredients that entered the transition rate. One of them was the transition amplitude squared. This is whatever states the Hamiltonian is capable of connecting you to. Initial state, final state squared. And then there's 2 pi delta function with a factor of h bar to make the units work. But it's just energy conservation and transition probability. That is Fermi's golden rule. We discussed it previously for the case when we had discrete quantum states, something like the individual discrete levels of the harmonic oscillator or the individual discrete levels of the hydrogen atom. We will discuss it today in a little bit different context when we are talking about a continuous density of states. So that will require, the right-hand side of this formula will be the same, but we will need to reinterpret the left-hand side a little bit. That was time-dependent perturbation theory and Fermi's golden rule. Also, we were discussing last week atoms in external fields. That included the Zeeman effect, which was the coupling of the orbital and spin angular momentum in the atom to the magnetic field. This is essentially a magnetic moment mu that wants to align with the magnetic field B. And there were 2 sources of that magnetic moment. One of them came from the orbital angular momentum. The other one came from the spin angular momentum. It looks almost like you're adding the 2 things together to get a total angular momentum, but the spin comes in with an extra factor of 2. This is the G factor because of the relativistic or the fundamentally spin 1/2 nature of the angular momentum. So they come in with unequal weights, which is why it doesn't end up being simply J dot B. So this was one interaction of atoms with external fields, orbital angular momentum coupling to the magnetic field. We won't really be discussing the spin component today. The other thing that we discussed in great detail was the Stark effect. That's the interaction of the electric field with the charge distribution in the atom. So the interaction is proportional to E dot R. And so the basic interaction was coupling to the dipole moment. If your system has an electric dipole moment, then it receives a first order shift in the Stark effect. That can become increasingly complicated at higher orders at excited states in the hydrogen atom, where you may have degenerate states and you have to consider linear combinations of them, which may have a dipole moment, even though each individual state may not. Okay, any questions about the topics that we discussed before? Today's discussion about the photoelectric effect will synthesize all of these ingredients together, and it will be our launching point into discussing scattering theory. Okay, if not, then the basic problem that we want to pose and discuss today is the interaction of the hydrogen atom, specifically in its ground state, with a time-dependent perturbation. That time-dependent perturbation comes in the form of a time-dependent electric and magnetic field. So this is an incoming electromagnetic wave. We will start today with a recap of the most important features from Jackson electrodynamics to remind ourselves how electromagnetic waves work. And then we will take that potential and we will couple it to the hydrogen atom in its ground state. And we will ask, what is the transition rate using Fermi's golden rule to go from the ground state to a free particle state? You could ask about a transition from the ground state to one of the excited states, but the photoelectric effect specifically deals with the ionization of the hydrogen atom. So we're going to liberate the electron and take it all the way out from the ground state up to a positive energy state whose energy E final corresponds to a momentum, P final squared over 2m. So that's the problem that we want to tackle. Before we get into the quantum mechanics of it, let us refresh ourselves on the physics of electromagnetic waves. Let me ask you guys before I dive into this, how recently have you taken E&M? I don't think grad E&M was offered here last semester. Is that correct?
Correct.
That's correct.
So you guys probably haven't seen this since undergrad. Yes?
Correct.
Correct.
Okay. So then that's good. We'll go through this refresher. Okay, so the starting point for this discussion is Maxwell's equations in vacuum. So in vacuum means I'm going to take the charge density rho to be 0, and I'm going to take the current density J to be 0. I'm also going to continue with the notation that we've been using. The system of units that's in Shankar used everywhere is Gaussian units or CGS units. All right, so there are 4 Maxwell's equations. The first tells you that the electric field, I'm going to use curly E for the electric field, hopefully I remember. Divergence of the electric field is proportional to the charge density. The electric field diverges away from a positive charge, it converges towards a negative charge. If there is 0 charge density in vacuum, then the electric field is neither diverging nor converging everywhere in space. The second is that the divergence of the magnetic field is fundamentally 0 everywhere. Unlike the electric field, which has monopoles, it has positive and negative point charges. The magnetic field does not. It can never diverge or converge ever. Similarly, we have curl of the electric field, which is related to the time derivative of the magnetic field. This is about magnetic induction. So this tells me if I have a time-dependent magnetic field, then I can induce an EMF, or I can induce an electric field that flows in a circle. So if I have a magnet going towards or away from a loop of wire, then it will create a circular electric field that will generate a current flowing along that wire. This is magnetic induction. The last one tells you curl of the magnetic field is related to the time derivative of the electric field. This tells you, now normally the right-hand side here contains a current density J. In a vacuum, that's 0. So that tells you if you have a wire with some current flowing through it, that current creates a circular curling magnetic field around the wire. Also, if you have a time-dependent electric field, like on a capacitor, where you have charge building up on one side and on the other side, that acts like a current. So a time-dependent electric field or an actual current creates a circular flow of the magnetic field. So these are Maxwell's equations, and in vacuum, this right-hand side is 0, this right-hand side is 0. There's no epsilon naughts and mu naughts here because we're working in Gaussian units. Okay, Maxwell's equations are lovely, but they are difficult to solve in all of their full glory. So one mathematical trick that we use is to explicitly implement 2 of them by introducing potentials. Introduce potentials to explicitly enforce 2 of these equations. The potentials that we introduce enforce this equation and this one. These 2 can have currents on the right-hand side, but these ones don't. So we will explicitly enforce this condition, and we will explicitly enforce this condition. The first thing that we will do is we'll introduce a vector potential. The magnetic vector potential A is defined such that the magnetic field B is defined to be curl of A. That's possible because any field, any vector field which does not diverge can always be written as a pure curl. So if B is defined to be curl of A, this is useful because then that means that this equation, divergence of B, is equal to divergence of curl of A. And this is equal to 0 for any A. So by introducing the vector potential and rewriting our equations in terms of A, we automatically guarantee that this condition is satisfied. Likewise, if I take that expression and I plug it in here, then this equation about magnetic induction allows us to introduce a electric scalar potential. So if I plug it into this equation, I have curl of the electric field plus 1 over c ddt of the magnetic field. We've already introduced curl of A equals 0. I have curl of something and curl of something. If I swap the order of the derivatives and I pull out the curl, this expression is telling me that the curl of something is 0. Curl of E plus 1 over c dA dt is equal to 0. So just like in this case, I have the divergence of something is 0, and I can always write that as a pure curl. Here I have the curl of something is 0. That means I can always write the thing that's being taken the curl of as a pure gradient. So this is a conservative field. It does not circulate. Its curl is equal to 0. So without loss of generality, I can always define some scalar function phi such that E plus 1 over c dA dt is defined to be negative gradient of phi, the scalar potential phi. The negative sign here is pure convention. When I do this, that automatically guarantees that this expression is curl of negative grad phi, and this is always equal to 0 for any phi. So by explicitly introducing the scalar and the vector potential, I automatically, by construction, satisfy 2 out of 4 Maxwell's equations. So that makes my life a lot easier, and I can write down the other 2 Maxwell's equations in terms of these potentials. All right, so then the remaining Maxwell's equations are so I have from Gauss's law, divergence of the electric field is equal to, in terms of the potentials, this is the divergence of, here, E is equal to negative grad phi minus 1 over C dA dt. And this is equal to 0. So if I take the divergence of this quantity, this is negative Laplacian divergence of the gradient of phi minus 1 over C dt divergence of A is equal to 0. And I can just trivially cancel the minus sign here. So I get Laplacian of the scalar potential plus 1 over C ddt divergence of the vector potential is equal to 0. This is now Gauss's law, the first Maxwell equation written in terms of the potentials. I'm going to leave this last one down here for a second because now we're going to plug in for this one too. The second Maxwell's equation is curl of B minus 1 over C dt is equal to 0. So this is equal to curl of A minus 1 over C ddt of the electric field, which is negative grad phi minus 1 over C dA dt. And this thing is supposed to be equal to 0. This equation is a bit more complicated, so let's break it down. I think it's easiest to see what's going on in this equation in terms of components. So let me write the same expression out in terms of components. So this first thing is a curl. So this is epsilon ijk derivative with respect to component j of this second thing is also a curl. So that is another epsilon klm derivative with respect to component L of vector potential index AM minus 1 over C ddt. This is minus derivative with respect to component I of the scalar potential phi minus plus 1 over C squared, or why don't I go ahead and cancel the minus signs here too, plus 1 over C squared, d squared, dt squared of index AI is equal to 0. So the way that I've set it up here is that this is an equation for each component I of the vector potential. AI here is free, derivative I here is free. I got a bunch of index mess here, but I is a free component, J is paired up, K is paired up, L is paired up, M is paired up. So this is an equation for each I. I can simplify this by using the algebra of the Levi-Civita symbols. So this expression here is epsilon ijk, epsilon klm, two derivatives, derivative J, derivative L on component AM. Now I use the identity of the Levi-Civita symbols. The repeated index here is K. So if I pair up the other indices in the correct order and in the wrong order, I get a set of Kronecker deltas. This is delta IL, delta JM minus the wrong order, delta IM, delta JL. So when I expand this thing, the first one is going to set component L equal to the free index I, and it's going to pair up J with M. So this first term is derivative I, derivative J, AJ, minus the second one has M set equal to I, which is the free index, and J set equal to L. So this is minus derivative J, also derivative J, AI. This is a way of writing, this is the derivative in the I direction of divergence of A, minus this object, the combination of two derivatives is the Laplacian of AI. This is a weird vector identity, which I think is easiest to see derived in terms of components like this. Okay, so plugging it back in, the second Maxwell equation, which is now the other independent constraint, gives me derivative I, divergence of the vector potential, minus Laplacian of AI, plus derivative I, I'm going to switch the order of these things, derivative I 1 over c d phi dt. Yes. Okay, plus 1 over c squared, second derivative with respect to time, d squared dt squared of ai is equal to 0. I'm going to group these terms together because two of these things look real friendly to me. This one and this one start to remind me of the wave equation. So I'm going to group those two things together. So this is minus Laplacian plus 1 over c squared, d squared dt squared ai, and then the piece that's left, all of it has a single gradient piece, di, plus derivative with respect to the ith component of divergence of a plus 1 over c d phi dt equal to 0. And then I'm just going to change the minus sign of everything. So this is Laplacian ai minus 1 over c squared d squared ai dt squared minus di divergence of a plus 1 over c d phi dt equal to 0. Okay, so we started with 4 Maxwell's equations. By introducing two potentials, the magnetic vector potential and the electric scalar potential, we have manifestly enforced 2 of them for free. And we have simplified the other 2. So that's one advantage of working with the potentials instead of working with the electric and magnetic fields. There's one drawback to working with the potentials, which is that the potentials are non-unique. So we explicitly enforced two out of 4 Maxwell equations. The con is potentials phi and A are non-unique. And they are very highly non-unique. They are infinitely non-unique. So the non-uniqueness of the potentials is expressed in the freedom of a gauge transformation. So if I start with any vector field A, and I form a new one, A prime, which is related to it by adding a gradient of a scalar function lambda. Curl of A gave me my magnetic field. Curl of A prime is equal to curl of A and curl of a pure gradient. Curl of a gradient is 0. So the curl of this field and the curl of that field are identical. These two vector fields will always produce the same physics, the same magnetic field. Likewise, if I also shift the scalar potential phi by a total time derivative, d dt, of that same function lambda, then I will always produce the same electric field. So the problem is this degeneracy, that phi prime and A prime produce the same E and B fields. As the original phi and A for any scalar function lambda. So the point is that these fields are not unique. There's an entire family of them. There's an infinite family of them. And you can transform from one of them to another one by just making up any scalar function you want and transforming the fields in such a way. So that is an advantage and a disadvantage. The non-uniqueness means you always have to grapple with, I can do the calculation, you can do the calculation, and we can both be right. But I can do the calculation and get one answer for A and phi. You can do the calculation and get a different answer for A and phi, and our answers can both be correct and can both be describing the same E and B fields, but I can't tell because our A and phi look different. So it's entirely possible to get two different solutions to Maxwell's equations that have the same physics but look very different. So this effect is called gauge freedom. And that also has both pros and cons. So let me start with the con. And have the same answer in the same electric and magnetic fields that looks very different. Pro is, if I have all of this freedom and any one of these things can solve Maxwell's equations, I can just make up constraints. So I can choose by my own free will any kind of constraints I want on A and on phi that use up this extra freedom. That is called fixing a gauge. I impose a condition of my choice that eliminates that freedom and uniquely specifies the potentials in terms of those fields. And choose conditions on A and on phi to eliminate the gauge freedom. And fix them uniquely. So this is called fixing a gauge. There are an infinite number of choices of different possible gauges. Some of them will be better choices than others, but all of them can work. They all correspond to the same Maxwell's equations, but some of them will make your life easier and some of them will make your life harder. That depends on the problem you're solving. So an intelligent choice of the gauge you want can drastically simplify the problem. So examples, you could choose something like AX equals 0 gauge. You could just decide to set a Z equals 0 gauge. You can just freely eliminate some degrees of freedom because the vector and scalar potential have too many of them. The one that will make our life the easiest is called Coulomb gauge. In Coulomb gauge, we choose the condition that the divergence of A is equal to 0, and we choose the condition that the scalar potential is equal to 0 everywhere in space. It takes some work to show that if I choose these conditions, that is legal. That if I choose this, that corresponds to specifying a particular lambda that I can always find. But it's true. When I do this, if I go back to the Maxwell's equations that we had left, you see why this is such an advantageous choice for us. In Coulomb gauge, the Maxwell equations that we had were first, Laplacian of the scalar potential plus 1 over c ddt, divergence of the vector potential is equal to 0. in Coulomb gauge, the scalar potential is 0, and the divergence of the vector field is also 0. So this equation becomes 0 equals 0 and is automatically satisfied. So that's nice. The other one is even better, because what we had before was Laplacian of AI minus 1 over c squared d squared AI dt squared minus derivative in the I direction, divergence of the vector potential plus 1 over c derivative with respect to time of the scalar potential is equal to 0. And now we have the slam dunk, because divergence of the vector potential is 0, scalar potential is also 0. So in Coulomb gauge, all of Maxwell's equations have boiled down to one thing. Laplacian of the Laplacian of the vector potential minus 1 over c squared, second time derivative of the vector potential, is equal to 0. This equation is one of the most important equations in physics. What is it?
Wave equation?
It is the wave equation. Very good. So Maxwell's equations always imply that the electric and magnetic fields in vacuum behave like plane waves, that there are plane wave solutions. But the advantage of choosing Coulomb gauge is that the vector potential is a plane wave solution. So you make that plane wave behavior completely manifest. It would always be there in any gauge, but this gauge makes it totally explicit. Okay, so we have the wave equation. How do we solve the wave equation? Also called, why is it called the wave equation? The easiest thing to do is to perform a Fourier transform. Then my derivative will just become a multiplicative factor. So if I have a component AI that depends on space and on time, I introduce a Fourier transform of both the spatial degrees of freedom and the time degrees of freedom. So I'm going to write this as a three-dimensional Fourier transform, d3k over 2 pi cubed, and also integral d omega over 2 pi. I'm transforming all 4 space-time variables. And let's see, my Fourier convention is e to the plus I k dot r, e to the minus I omega t. And then in general, I have some Fourier component AI that depends on the wave vector k and on the frequency omega. Now, to be completely clear, for the rest of this class, when I talk about k, I'm going to be talking about this k. This is the wave vector of the Fourier transformed vector potential. That's not the same thing as the unit vector k along the z-axis.
Sorry, just to be clear, the first exponential is I k dot r?
Yes, e to the positive I k dot r, e to the negative I omega t.
Okay, thank you.
Yes. Wave vector k, not unit vector, you could call it k hat. Okay, so if I take this decomposition, this Fourier transform, which is an exact statement, and I plug it back into the wave equation, then everything here, I have this integral transform that comes out in front of everything, d3k d omega over 2 pi to the 4th. If this looks like 4-dimensional space-time, it's because it is. And then this equation is now Laplacian minus 1 over c squared second time derivative, acting on this part. The spatial dependence is fully contained in e to the I k dot r. The time dependence is fully contained in e to the minus omega t. And then I've got that Fourier component AI of k and omega equal to 0. So I've just plugged in the Fourier transform into my wave equation. This is advantageous because this del squared only hits this Fourier factor. And this time derivative here only hits that Fourier factor. None of them have anything to do with that Fourier constant here. So this expression gives me integral d3k d omega over 2 pi to the fourth. When I take these derivatives, I get the same exponentials back, e to the I k dot r, e to the minus I omega t. And now I end up with, when I take a derivative, I bring down a factor of I k, and then I do 2 of them. This is a dot product. So I get minus k squared. Same thing here. Now I take a time derivative, I bring down a factor minus I omega, and I do 2 of them. Plus omega squared over c squared. A tilde of I of k omega equals 0. And so the answer is any Fourier component solves this equation. Any AI of k and omega solves Maxwell's equations if k squared equals omega squared over c squared. So this is what tells you that the plane waves travel at the speed of light. In terms of quantum mechanics, this gives us a relationship between the momentum and the energy of a plane wave. So in terms of a photon, a single mode, AI of k and omega, then we will say the energy of the photon, especially in terms of time-dependent perturbation theory, where this is the energy that will be absorbed by the hydrogen atom. The energy is h bar omega. The momentum is given by the de Broglie wavelength of the photon, which is h bar k. So this is, let's say, E sub gamma, the energy of the photon. This is the momentum E sub gamma of the photon. And this constraint tells me that the energy of the photon, so let me write it this way, h bar squared omega squared equals h bar squared k squared c squared. And if I write this in terms of the energy and the momentum, this says energy of the photon squared equals momentum of the photon times c squared. So this is similar to the Einstein relation in special relativity. Squared equals pc squared plus mc squared squared for a massless photon, where this second term is 0. Okay. So we have solved Maxwell's equations. We have shown that in vacuum, Maxwell's equations emit plane wave solutions. We will consider a plane wave which is just one of these modes. Really, I guess it's 2, if we want a real valued plane wave. So we will consider I'll call it 1 in quotes Fourier mode. A pure plane wave, A of R and T is some constant vector A naught, cosine k dot r minus omega t. I say 1 mode in quotes because, of course, cosine can be written as a sum of 2 exponentials, e to the plus I omega t, e to the minus I omega t. So it's really 2 pure modes that are complex that I'm adding together to make 1 mode, which is real. All right, if this is my vector potential solution, what does that give me for my electric and magnetic fields? The electric field associated with this, E of R and T, was minus grad phi minus 1 over C dA dt. In Coulomb gauge, the scalar potential is 0. So the electric field in Coulomb gauge comes entirely from the time derivative of the vector potential. If I take the time derivative of this thing, cosine turns into sine, and I bring out a factor of omega. So I get, let's see, I have a minus 1 over c. I get another minus when I turn cosine into negative sine, and I have a third minus when I have chain rule with minus omega here. So at the end of the day, I get minus omega over c a naught times sine k dot r minus omega t. What about the magnetic field? The magnetic field is given by curl of the vector potential, always and forever. If I take this thing and I take the curl of it, that is a derivative cross product. The derivative hits this factor, and the cross product becomes k cross a naught. The derivative turns cosine into negative sine, just like before. So I get negative k cross a naught sine k dot r minus omega t. So altogether, what does this tell us about this electromagnetic wave? It has magnitude of the electric field, E naught, given by this absolute value, omega over c a naught. So what that tells us is in this gauge, A is parallel to the electric field. So when we do the calculations later in terms of A, think in the back of your head, A is pointing in the direction of E. At least along the correct axis. There could be a positive or negative sign depending on time, but it gives you the correct axis. The magnetic field B has a magnitude, which is K cross A. If E is in the direction of A, then K cross A is perpendicular to E. Electric field perpendicular to the magnetic field, and these are all both mutually, and both of these are mutually perpendicular to the wave vector K. The gauge condition that we started off in, the Coulomb gauge condition was that divergence of the vector potential is equal to 0. If I take this expression and I take the divergence, the derivative gives me again K and a negative sign, dot product with A naught. So I get negative K dot A naught sine K dot R minus omega T. This has to be 0 always and forever in this gauge, not just at some magical time. So the only way to guarantee that this is true is if K dot A naught is equal to 0. So this is our picture of the wave. We have an oscillating electric field. Going up and down in some plane. The magnetic field, B, is perpendicular to this, so it's oscillating in and out of the board. These two are in phase. They both oscillate like sine omega, or sine K dot R minus omega T, both for B and for E. The vector potential A is parallel to parallel to the electric field E. And both of these are perpendicular to the actual direction of propagation, which is the wave vector K, or to put it more physically, it is the momentum vector P of the photon, which is h bar K. And the energy E of the photon is h bar omega. So this is our plane wave. This is the initial condition. We want to consider what is the impact of this time-dependent electromagnetic wave on the hydrogen atoms starting in the ground state. So now we can finally pose the problem. We want to consider the transition induced by this wave starting in the 100 or 1s state. And we want to calculate the transition rate using Fermi's golden rule that takes this electron from the ground state and promotes it up to a free particle state up here with positive energy. E final is P final squared over 2m. All right, any questions on the review of E&M, the posing of the problem? Now we have all the tools that we need to evaluate this using time-dependent perturbation theory. Was this stuff fairly familiar to you guys, or was some of this stuff new?
This was all mostly review.
I can't hear you very well.
This was all mostly review for me.
Mostly review. Okay, good. Okay, so let's put down some more information to pose the problem. We're going to need to specify clearly what are the initial state and what are the final state to be able to calculate the transition amplitude and to use Fermi's golden rule. So the initial states, if I write down the wave function, that is the projection onto a specific position of the 100 state. If I look up the expression in Shankar, this is psi 100 of r, and this is 1 over square root of pi Bohr radius cubed, just a decaying exponential, e to the minus r over Bohr radius. Likewise, the final state is the plane wave, the free particle, with momentum pf written in a position basis. This is 1 over 2 pi h bar to the 3 halves, e to the plus I over h bar p final dot r. Okay, before we dive in and we start calculating transition rates using Fermi's golden rule, we need to say a few words about the fact that now we are talking about the transition from a discrete state to one of a continuous number of states. That requires a little bit of reinterpretation of what the transition rate means. Calculated our final initial for discrete states that are normalized to 1. So that if you have two different states, n, m, this is a Kronecker delta of n and m. The momentum eigenstates, the plane wave basis, are part of an infinite family. So you can't talk about a Kronecker delta in those states. You have to talk about a Dirac delta function. Three-dimensional Dirac delta function of p prime minus p. So that means that whereas in the discrete case in quantum mechanics, we've been talking about probabilities, things that add up to 1. In the continuous case, we're really talking about probability densities, things that integrate to 1. So then you have something like a discrete probability, P final initial as a function of time, and then that transition rate, R final initial, was the limit T going to infinity of P final initial over time. For the continuous case, we're talking about a probability density, a probability which is differential in that final state momentum. So that if I integrate over all momentum, I can normalize it to 1 by integrating over the delta function. So this object is still a function of time, but the transition rate now I'm talking about is really a transition rate density. So this is dr, d3p final, which is the limit T going to infinity 1 over time times that probability density, D probability D3P final of T. This conceptual difference is going to be important because it's going to allow us to ultimately integrate over the delta function that we get from Fermi's golden rule. So Fermi's golden rule for this system is that the transition rate, which is now a rate density, dr d3pf, is 2 pi over h bar. Transition amplitude, the final state is momentum eigenstate pf times my perturbing Hamiltonian times the initial state, which was 1, 0, 0 squared, delta function of E final minus E initial minus H bar omega, only if I'm talking about a potential which was E to the minus omega t. Otherwise, I have to subtract the energy instead of adding it. So this is how we're posing the problem. The next question is, what is my Hamiltonian for this interaction? So this involves both the E and B fields. So a combination of both the Stark effect and the Zeeman effect. Although we're not going to write it in a way that manifestly shows either one. The easiest way to get this in terms of the vector potential A is through minimal coupling. We've done this before several times. So recall that if I have a free particle, H free, is P squared over 2m. Minimal coupling means I take the momentum P and I turn it into P minus charge over C vector potential. Especially in this gauge where the scalar potential is 0, that's the only change. So for a particle which is charged moving in an external field, then the Hamiltonian becomes P minus Q over CA squared over 2m. And if I expand this, then I get the first cross term as my interaction. So H1 is minus Q over 2mc P dot A plus A dot P. It's worth noting that this is an approximation, that if I actually expand this quadratic combination, there's also an A squared term. That is being neglected here as higher order in perturbation theory. Okay, now in general, my momentum is an operator in quantum mechanics. If my vector potential knows about position, it can also be an operator. So these guys do not necessarily commute, which is why I kept both terms. But I can always add and subtract the same thing. So I can write this as Hamiltonian equals, let's say, now Q is negative E, so this is plus E over MC, A dot P. Plus the price that I pay for swapping the order as a commutator, 2p, let me write it as pi, so I get that dot product explicitly, ai. But I know something about this commutator. If I write this commutator in position space, this is minus IH bar commutator of derivative I on the vector potential AI. That commutator is a difference of two terms. This is the one where the derivative acts on A and whatever comes after, minus the thing where derivative acts only on the thing that comes after. So by product rule, this commutator gives me just the part where the derivative acts on A. Minus IH bar derivative I AI. But this is just divergence of A. And this whole thing is zero in Coulomb gauge. So in general, P and A do not necessarily commute with each other. But in Coulomb gauge, they do, because that divergence is equal to zero. So this is the Hamiltonian that we're going to use. E over MC A dot P. H1 of T is E over MC A of T dot P operator. And if I plug in the specific form of this potential, this was E over MC. A was a constant vector A naught times a cosine. That's cosine K dot R, which is an operator, minus omega T. And then a constant vector A naught dot P, which is an operator. I'm almost at the form that I can apply Fermi's golden rule. Now I need to split this cosine up into e to the I omega t and e to the minus I omega t. So if I split this cosine apart, this is e over 2mc. I have one term, which is e to the plus I k dot r, e to the minus I omega t, plus the other combination, e to the minus I k dot r, e to the plus I omega t. And the operator that's left is A naught dot P. So this is two combinations of operators. If I split it up explicitly, I have E over 2mc. The first operator is E to the I, K dot R, operator R, A naught dot P, E operator. This operator comes with the time dependence, E to the minus I omega t, plus the complex conjugate of this thing, e to the minus I k dot r, r operator, a naught dot t, with the opposite time dependence, e to the plus I omega t. For each of these modes, I know exactly how to apply Fermi's golden rule. So I've got e to the minus I omega t, e to the plus I omega t. One of these adds energy to the atom, one of them subtracts it. Which one subtracts energy?
The one with the positive I omega t?
Yes, e to the positive I omega t is going to subtract energy away from the hydrogen atom. If the hydrogen atom starts off in the ground state, what's going to happen with this term?
It's zero.
Zero. It's already in the ground state. I can't subtract energy away from it. This thing is, if I had the hydrogen atom in an excited state, I would have equal probability to add energy to it or subtract energy from it. But if I start off in the ground state, I can't subtract energy from it. This piece is going to give me zero because it will be impossible to ever fulfill this delta function. So for our purposes, we can just forget about it. This term would subtract energy. We have E final equals E initial minus H bar omega. And this cannot be true for the ground state. So for our purposes, I'll leave Fermi's golden rule right here. We only need to consider the positive energy piece. That's the only thing that's going to add energy in that is capable of exciting the electrons to freedom. So we will take H1 of T is E over 2mc e to the I k dot r operator, a naught dot T. e to the minus I omega t. And that's going to have exactly this form when we plug it into Fairness Golden. Everybody with me so far?
This is only for in first order, right? Because in second order, the ground state can be reduced.
Yes, very good. So all of this is valid only to first order in perturbation theory. That is correct.
Okay.
Yeah, first order in perturbation theory only for the ground state only. Either of those things would change this conclusion. That's correct. Okay, now we have the ingredients that we need to plug it in. We have the energy conserving delta function, and we have the transition matrix element. The rest of the exercise is going into calculating exactly this beast. All right, so let's work it out. Oh, okay, so we have P final. The time independent part, so it's just this thing. The e to the minus I omega t went into that delta function. Times 1, 0, 0. Let's write this as an integral over the wave functions at a position basis. So I have a bunch of constants out front. I have e over 2mc coming from the Hamiltonian. I have 1 over square root of pi Bohr radius cubed coming from the 1, 0, 0 state. I have 1 over 2 pi h bar to the 3 halves coming from the plane wave state. Whole bunch of constants that, for my purposes, to avoid carrying them around everywhere, I'm just going to call them n, starting from now. The business end of this calculation is the integral d3r. This wave function was e to the plus I p dot r, but now it's a bra, so I have to complex conjugate it. So I have e to the minus I over h bar, p final dot r. The Hamiltonian itself was e to the plus I k dot r, a naught dot p. In a position basis, this is minus I h bar gradient. And now the plane wave, the hydrogenic ground state 1, 0, 0 was just e to the minus r divided by Bohr radius. So 3 ingredients, e to the minus I over h bar, p dot r, that's the plane wave state, p final. The Hamiltonian was e to the I k dot r, a dot p. P is minus I h bar gradient in a position representation. And the state 1, 0, 0 is just the decaying exponential, e to the minus r over Bohr radius. Okay. All right, so I have some overall coefficients n in front. I have minus I h bar, integral d3r. I'm going to combine these two phase factors. There's no point in keeping them separate. They both have exactly the same form. So I'm going to write this as e to the minus I over h bar, p final minus h bar k dot r, gradient of e to the minus r over Bohr radius. Now, if I wanted to, I could take the gradient directly of the Bohr radius, of this decaying exponential. But it's much easier to integrate this thing by parts. So I will integrate this by parts and allow the gradient to act instead on the Fourier factor, and that will give me something simple. Before I do that, let me make a comment about the momentum that shows up here. This object has physics in it. This is telling me I started off with my hydrogen atom, and then I hit it with a photon, some electromagnetic wave. The photon carried momentum h bar k. I measured it coming out with some momentum p final. So this object, the momentum that I measure at the end, minus the momentum that I added, it's logical to call this the initial momentum, pi. P final minus h bar k. This is the momentum of the object before it got hit by the photon. So for the rest of this derivation, when I say Pi, this is what I'm referring to, the measured momentum P final minus the momentum that's been added to it, H bar K. So with this in mind, now I can integrate by parts. P final H1 100 equals, I have N. I had minus I H bar. When I integrate by parts, I'm going to get a minus sign that makes it plus I H bar. Integral D3R. After integration by parts, now the gradient acts on the Fourier factor. Gradient of e to the minus I over H bar P initial dot R. E to the minus R over Bohr radius. In principle, there's also a surface term or a boundary term that comes when you integrate by parts. That surface term is 0 because the decaying exponential gives me 0 when R goes to infinity. So the gradient acts here on this space factor, and I just bring down a factor of minus I over H bar P initial. That gets, I lost my factor of A naught somewhere. This was A naught dot product with this thing. So when I take this derivative, I bring down a factor of minus I over H bar P initial, and I get the same phase factor back, minus I over H bar P initial dot R. So the minus I over H bar exactly cancels the plus I H bar, and then I get A naught dot P initial. D3R, e to the minus I over H bar, P initial dot R, e to the minus R divided by Bohr radius. Okay, there is physics in this expression. What kind of object is this integral? Ever seen an integral like this before? E to the minus I something dot R times a function.
A Fourier transform.
Fourier transform. The Fourier transform for the time-dependent perturbation theory was a Fourier transform in time. And that Fourier transform in time told us about energy. We said that the e to the minus I omega t perturbation was adding energy. This is a Fourier transform in space. And it's no accident that that is related to momentum. So this is telling us about, I had momentum h bar k coming in. My target is a superposition of different momentum states. Pi, it's a superposition of all of them. The distribution of that momentum is obtained by exactly a Fourier transform of the spatial wave function. So this is the spatial wave function being transformed into, let's say, psi 100 of p. And so what we're doing in this scattering problem is picking out a particular mode, Pi, this one, that then gets hit by h bar k and becomes P final equals P initial plus h bar k. This is conservation of momentum. This is, again, the foundation of what we will build going forward in scattering theory. So how do I Fourier transform the decaying exponential? There are a few ways to do it. Given that I have 3 minutes, I think I will take a shortcut. So if I write out this integral in spherical coordinates, this is integral dr times r squared from 0 to infinity. Integral d theta sine theta from 0 to pi, integral d phi from 0 to 2 pi. If I choose the z-axis to be the direction of P initial, then this is e to the minus I over h bar. P initial r cosine theta. E to the minus r divided by Bohr radius. So when I do the phi integral, I trivially get a factor of 2 pi. That's good. The theta integral is easier to convert into cosine theta. This is integral of derivative of cosine theta from minus 1 to plus 1. Cosine theta is exactly what occurs up here. So if I integrate d cosine theta from minus 1 to 1, e to the minus I over h bar, p initial r cosine theta, then when I integrate this thing, I get 1 over the prefactor, 1 over minus I over h bar, p initial times r. And then I get the exponential back evaluated in the limits, plus 1 and minus 1. So I get e to the minus I over h bar, p initial r from plus 1 minus e to the plus I over h bar, p initial r. All right, almost done. Final H1 100 is normalization constant A naught dot P initial. From doing this, now I have integral dr times r squared, 0 to infinity. From doing, I also have a factor of 2 pi. From doing this one, I have, let's see, let's call it IH bar over PIR times e to the minus I over h bar PIR minus e to the plus I over h bar PIR. All right, A naught dot PI 2 pi IH bar over PIR. We're in better shape now. Oh, and I forgot e to the minus r over Bohr radius. Now I can combine these two things. I have 1 over r cancels one of these powers of r. Integral 0 to infinity dr times r times the combination of the exponentials. E to the minus I over h bar. E to the minus, how about this way? I over h bar pi plus 1 over Bohr radius r minus e to the minus e to the plus I over h bar p initial minus 1 over Bohr radius r. Yeah, I think that's fine. Minus added. Yes, okay, very good. So you could do this integral by parts. Another easy way to do it is to write this as a derivative with respect to 1 over the Bohr radius. That's a clever way to bring down this extra factor of r. Maybe 1 over Bohr radius. I am out of time, so let me just write the answer. At the end of the day, what we get is final H1 100 equals big long mass denormalization constant. E over 2mc 2 pi h bar to the 3 halves square root pi or radius cubed times a naught dot the initial. And the result from the integration is 8 pi or radius cubed h bar to the fourth 1 over h bar squared plus p initial squared or radius squared squared. Okay, great. So we have now done the difficult calculation of evaluating the transition matrix element. The last step that we will carry out next time is to plug this into Fermi's golden rule and evaluate the transition rates. That will ultimately lead us to defining something funny called a cross-section, which is the elementary observable that we will calculate all the time in scattering theories, the natural way of describing the transition rate per unit current. So that's what we will do next time, and this will be a nice bridge into scattering theory and other systems. Any questions? All right, thank you guys very much.
Thank you.